तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we have familiarized ourselves with some symmetry conditions relating to the Fourier coefficients. We would like to continue this discussion with an example where we make use of the symmetry conditions and use them to calculate the various Fourier coefficients quite effectively. Consider this example where we are dealing with an f of t which is a half wave rectified sine wave of amplitude a and a fundamental period t naught. Now when you look at this waveform does not have either an even symmetry or an odd symmetry. You recall that we had observed earlier that any given function can be split up as its even part and odd part respectively. In other words, if you have an f of t, if you break this up as f of t plus f of minus t divided by 2 plus f of t minus of f of minus t upon 2, this becomes the even part and this becomes the odd part. Because when you change t for minus t, the value of this part remains unchanged. But if you substitute minus t for t, the value of this function gets reversed. Therefore, any f of t can be split up into its even part and odd part respectively in this fashion. And when you do that, sometimes you will find some additional symmetries which are not present in the original waveform. Let us see how this goes. Suppose this is f of t, then let us construct what f of minus t would be. The sequence of values which this function takes for positive t, it will assume in the reverse direction. Therefore, you have corresponding to this and another loop corresponding to this on the negative side. And corresponding to this, you have a loop like this and it goes on like this. This is f of minus t. To get the even part of the function, then we have to add up these two waves and then divide by 2. So if you do that, then what you have is whenever this is blank, you have this half cycle of sine wave. Whenever this is blank, this is a half cycle sine wave you have got. Therefore, you have like this, where the amplitude now, the peak amplitude is a, but you are dividing by 2, this becomes a upon 2. And this is the even part of this. On the other hand, if you subtract f of minus t from f of t and divide by 2, you get the odd part, f of t minus f of minus t upon 2. So when you subtract the second waveform from the first, this gets reversed, the sign gets reversed, therefore this becomes a negative half cycle and this also becomes a negative half cycle, and therefore these negative half cycles fit in smugly into these blank intervals. And the result is that you have a waveform like this, which is a pure sine wave because each half cycle sine wave is reproduced in the proper direction here, and this is f of the odd part of t, f naught t. So now if you look at this constituent parts FET and F naught t of your original f of t, you immediately observe that there are symmetries here. For example, f naught of t is certainly a pure sine wave, therefore there is no Fourier series expansion necessary for that. That itself constitutes the entire Fourier series, a naught by 2 sine omega. So this will be a naught upon 2 sine omega naught t. But as far as the even part is concerned, you observe that this has got what we described as a kind of half wave symmetry. The function repeats itself every half cycle. And you also recall that we mentioned in the last class, this last lecture, that whenever you are having a waveform like this, we would like to still to continue this as the basic period, not as this, because we are going to relate this basic period to the parent waveform from which it is generated. After all, we want to talk about fundamental frequency in relation to this. Therefore, we continue to have the same fundamental frequency when describing this waveform as well. Consequently, we regard this as the basic period, in which case the function f of t happens to be f of t plus t naught upon 2. Therefore, this will have only even harmonics present. And since the function is even, only sine terms, only cosine terms will be present. So if you make the Fourier series expansion of this and add to this the Fourier series expansion of f naught of t, which is this, then you get the Fourier series for the entire function. So let us do this. Fe of t, suppose, as a DC term, the average value of this, as you know, any sinusoid, we are talking about the absolute average value 2 upon pi, that is the DC term, plus you have an cos n omega t, where you need to have n even only, because odd values of n would be absent because it contains only even harmonics. To calculate an, you take twice the average of the function 0 to t naught f of t cos n omega naught. And it can be shown that the contribution coming from this integral for 0 to t naught by 2 will be the same from t naught by 2 to t naught, provided n is even. Exactly the same arguments which we used in discussing the half wave symmetry case, where we have odd harmonics present. Exactly the same way we can show that this is equal to 4 upon t naught 0 to t naught upon 2. That means we are taking the average of this function over half cycle, f of t cos n omega naught t dt for n even only. You see, this particular formula will not be valid for n odd. I will not go to the resulting integration. It can be shown that this will lead to minus 2a upon pi n squared minus 1, that is the value. So finally, the Fourier series expansion for this can be written. I will write it here. So the Fourier series for this waveform would be f of t equals the DC term a upon pi plus the fundamental term which comes from the odd part a upon 2 sin omega naught t plus the remaining terms in the Fourier series expansion of the even part of the function, which will be minus 2a over pi times n squared minus 1 cos n omega naught t for n even starting from n equals 2 onwards. So you observe that even though this function as such does not appear to have any of the symmetries that we have talked about, by splitting this up into even and odd parts, you are able to find some symmetry at least in one of those parts, and the other of course falls out, it just breaks down into a single term. So it would be sometimes worthwhile for us, before we proceed to get the Fourier series expansion of any waveform, to see if we can produce some symmetries by resolving this function into its various constituents, one of them being probably the even part and the odd part respectively. You can think of other ways of resolving this, but we need to confine our discussion only to this. Now let us use this work that we have done here to work out another example where such a waveform is applied to an electrical circuit. In this example, we will consider that a waveform of a voltage of this shape is applied to an RC circuit and the voltage across the capacitor is taken to be the output voltage. So we will imagine that the peak value of this half wave rectified sine wave is 100 volts. Now this voltage is applied across the RC circuit, and we are interested in finding out the significant harmonics both at the input and the output voltage. So the problem is find the amplitudes of the significant harmonics in Vi and the output voltage V0. The data that is given R, let us say, is 1000 ohms, C 15.9 microfarads, and omega naught corresponding to this period T naught is 100 pi radians per second, which means the fundamental frequency is 50 hertz. Now since this input waveform is not sinusoidal, we can't apply straight away the phasor methods for calculating the output voltage. On the other hand, the Fourier series tells us that such an input voltage can be decomposed into a number of sinusoids, and so for each one of the sinusoidal components we can find out the corresponding output using the Fourier, using the phasor methods, and superpose all the solutions to obtain the output. Or in the problem like this, we are only interested in knowing the magnitudes or the harmonic components in the output voltage V0. So for each harmonic we can apply the phasor notation and the phasor algebra. Now we know that Vi can be expressed by means of Fourier series using the formula, using the result that we have obtained in the previous example when we considered just this kind of wave, half wave rectified sine wave. The answer there was, if you substitute the numerical values, will turn out to be 100 upon pi, that is the DC component, plus 50 sine omega naught t, that is the fundamental, and in addition we have a number of even harmonics. The first two even harmonics are the second harmonic and the fourth harmonic. This will be 3 pi and this is 200 by 15 pi cos 4 omega naught t. So for each one of these plus other terms which are insignificant, which we will ignore. For each one of these we would like to find out the output corresponding output quantity, and to do that we must find out the output voltage to the input voltage ratio as a function of frequency. So the system function in this case Hj omega by potential divider action is 1 over j omega c divided by r plus 1 over j omega c, that will be 1 over 1 plus j omega cr. This is the general system function as a function of frequency omega, but we are interested in evaluating this for particular values of omega, which are omega naught, 2 omega naught, 4 omega naught, and so on. Consequently, we will find out h j n omega naught for a general n. This will be 1 over 1 plus j n omega naught cr, which when you substitute the numerical values for r, c and omega will turn out to be 1 over 1 plus j 5n. In particular, we are interested only in the amplitudes of the harmonics, so we are not really interested in the angle associated with h of j n omega naught. So we would like to know only the magnitude in our problem. This will be therefore the 1 over square root of 1 plus 25 n square. So we know the amplitudes of each one of these harmonic terms, we know the magnitude of the system function. Now therefore we can find out the amplitudes of the output voltage. We can do it, we can organize it in this fashion. The amplitudes of DC, of course DC there is only one quantity, we do not have to talk about amplitude, but we can talk about the amplitude of the fundamental component, the second harmonic and the fourth harmonic. These are the significant harmonics that are present. So the input voltage as a DC component which is 100 upon pi, that is 31.8 volts. The 50 cycles component is 50 volts. The 100 cycles component is 200 upon 3 pi, that is 21.2 volts. And the 200 hertz component is 200 upon 15 pi, that turns out to be 4.24 volts. So these are the amplitudes of the different harmonic components as far as the input is concerned. And the value of the system function, when you apply a DC output input here, the same DC comes out across here because there is no current passing the circuit, and therefore that is equal to 1. The input output ratio is 1. In the case of the fundamental, n equals 1, therefore this is 1 over square root of 26. Case of second harmonic, n equals 2, therefore this will be 1 over square root of 101. And in the case of the fourth harmonic, n equals 4, so 16 times 25, 400, this is 1 over 401, square root of 400. So when you multiply these amplitudes with the corresponding magnitude of the system function, as far as the output is concerned, the various components will turn out to be this multiplied by this 31.8 volts. The 50 cycles component turns out to 9.8 volts, 100 cycles 2.11 volts, and this is 0.21 volts. So this RC circuit here essentially acts as a filter. You have an input voltage which is non-sinusoidal, which is a rectified sine wave, half wave rectified sine wave, and we would like to have a filter like this to swamp out the ripples. So all the AC components should be reduced to the extent possible, and we would like to have the output to be as pure a DC as possible. Now how good is this filter? Let us see. In this case, in the fundamental, in the input we have 38.1.8 volts DC, but the harmonic components are quite substantial, 50 volts fundamental, 21.2 second harmonic, 4.24 fourth harmonic. But as far as the output is concerned, the harmonic amplitudes are brought down considerably compared with the DC. Therefore, this is a good filter as far as the suppression of the various harmonic components are concerned. We had set up the Fourier series earlier in terms of trigonometric functions. Now there is an alternative way of setting up the Fourier series. This will be in terms of exponential functions. Let us proceed to do that. In terms of exponential functions. You recall that f of t we had written in terms of trigonometric functions as a naught plus the sum of cosine terms plus bn sin n omega naught t sum of sine terms. Now we can express sine and cosine terms in terms of exponential functions. So I can write this as an e to the power of jn omega naught t plus e to the power of minus jn omega naught t divided by 2 plus bn e to the power of jn omega naught t minus e to the power of minus jn omega naught t divided by 2j. N from 1 to infinity. Now we have a e to the power of jn omega naught t terms here as well as here. So let us group them together so that we write this series in terms of exponential functions. So you have a naught plus what is the coefficient of e to the power of jn omega naught t? an upon 2 plus bn upon 2j. So I can write this as an minus jbn upon 2. This is the coefficient of e to the power of jn omega naught t. N ranging from 1 to infinity. We also have terms like e to the power of minus jn omega naught t. And what is its coefficient? An upon 2. And then because the negative sign here, it is plus jbn upon 2. N from 1 to infinity. So what we have done is we express f of t not in terms of trigonometric functions but in terms of exponential functions of the type a j e to the power of jn omega naught t. Now we would like to, in the context of expansion in terms of Fourier exponential functions, we would like to indicate the coefficients in a different way. So we will call this Cn, a complex number Cn, and this will be Cn conjugate. And since we are calling the exponent in the coefficients, given the symbol C for the various coefficients, we may as well call this C naught. Therefore I can write this as C naught plus n from 1 to infinity, just to indicate that this is a complex number Cn, I will put a line on top, that is a complex coefficient, e to the power of Jn omega naught t plus n from 1 to infinity, this is Cn conjugate, because this is an minus jbn upon 2 is Cn, this is its conjugate, the angle, the imaginary part has its sign reversed, e to the power of minus Jn omega naught t. So, let us define Cn star as C minus n. Then we have f of t as C naught plus Cn e to the power of Jn omega naught t, n ranging from 1 to infinity, C minus n e to the power of minus Jn omega naught t. Now, we would like to combine these two summations into one. That can easily be done by substituting minus n for n here, in which case
minus infinity.
when you substitute minus n for n here, then I can write this as C naught n from 1 to infinity Cn e to the power of Jn omega naught t. So, when you change the dummy sign of summation minus n by n, therefore, this n goes from minus 1 to minus infinity. This is Cn e to the power of Jn omega naught t. Combining these two, I can write n from minus infinity to plus infinity, including this 0, minus 1 to infinity, minus infinity to minus 1, 0 and 1 to infinity, Cn e to the power of Jn omega naught t. This is f of t, where we observe that C minus n is Cn conjugate, which is An plus Jbn upon 2, because Cn conjugate is An plus Jbn upon 2. So, this is a very compact way of representing the Fourier series. You do not have two groups of terms like A coefficients and B coefficients, you have only to deal with a single set of coefficients Cn. The question is, how is the Cn related to An and Bn? That we already have seen, that Cn equals An minus Jbn upon 2. And in anticipation of this, suppose I take the magnitude of Cn, it is Cn square root of An squared plus Bn squared upon 2, or in other words, square root of An squared plus Bn squared equals 2Cn. So, in anticipation of this notation only, when we put the Fourier series expansion of a function in trigonometric form, trigonometric functions, we said the amplitude of the nth harmonic is 2Cn rather than Cn. It is in anticipation of this formula. Now, the next question that we would like to ask is, how do we evaluate the Cn coefficients? What is the formula for that? In the same way as we have done for the trigonometric functions, how do we get this complex coefficient Cn directly from the f of t? This can be easily derived as follows. Cn we know is An minus Jbn upon 2. And we know the formulas for An and Bn. Let us substitute that. This is half of An is 2 upon T naught f of t cos n omega naught t dt over a period. And for Bn, I can write 2 upon T naught f of t sin n omega naught t dt. This j term comes from here, this half of course is substituted here. Now these two integrals can be combined. First of all, I can take a 2 by t term, t naught term outside, so 1 upon t naught, 0 to t naught, f of t cos n omega naught t minus j sin n omega naught t and this we know is e to the power of j n omega naught t. So the integral that needs to be carried out to evaluate Cn is like this. This is really the average of f of t multiplied by e to the power of minus j n omega naught t. What do we observe here? And what are the merits of this exponential function, the exponential form of the Fourier series? First of all, we observe that we have only one single formula for evaluating the various Fourier coefficients. You don't have separate formulas for a0, an and bn. And the notation is very compact. More importantly, when we extend this concept of Fourier expansion of periodic functions to aperiodic functions, what we will refer to as Fourier integral concept, which we will take up later. There, these expressions for Cn can be, in a more straightforward fashion, extended to the Fourier integral concept than if we had persisted with an and bn. So we have a single formula valid for all n. The notation is compact, and the notation can be extended to the Fourier integral quite conveniently. That is the important thing. So in the Fourier expansion for this, we note that each term by itself may not convey to us any physical signal, because when you substitute a value, real value of time, this does not, by each term by itself will not yield a real value of the function. However, we have to bear in mind that if you take Cn e to the power of j n omega naught t and combine this with C minus n e to the power of minus j n omega naught t, these two together will lead to a real function of time, a sinusoid, which will be 2Cn cos n omega naught t. This one. We can easily show that. So the amplitude of the nth harmonic component is 2Cn, and this real function of time comes by combining the two exponential terms for plus n and minus n respectively. So individually it is not a physical signal, but when you combine these two, this is the conjugate of this, you will get this. Right. Now let us work out an example illustrating the exponential form of Fourier series. we take the same example that we have worked out earlier, a square wave, because we can compare the results. So this is f of t. We would like to find out the Fourier series expansion in exponential form. So Cn would be, easy way to remember would be average of f of t multiplied by e to the power of minus jn omega naught t. This is what we have to find out. So that will be 1 over t naught, and to find out the integral of project, we split this up into integral in two parts, one from 0 to t naught upon 2 and the other t naught upon 2 t naught, because the value of the function changes in these two intervals. Therefore, I can write this as
10 minutes left.
1 over t naught zero to t naught upon 2, the value of the function is a, e to the power of minus jn omega naught t dt, plus t naught upon 2 to t naught, and in this interval the value of the function is minus a minus jn omega naught t dt. So I take the a outside, a upon t naught, the first integral will yield e to the power of minus jn omega naught t by minus jn omega naught, minus, because of this minus sign here, e to the power of minus jn omega naught t divided by minus jn omega naught, and the first integral is evaluated between 0 and t naught upon 2. The second integral is evaluated between t naught upon 2 and the t naught. So you can take out minus jn omega naught outside, and if you evaluate this, it will be e to the power of minus jn at the upper limit. Omega naught t naught upon 2 is pi minus jn pi. At the lower limit it is 1 minus 1, and minus at the upper limit it is minus jn omega naught t naught is 2 pi. Therefore e to the power of jn 2 pi, it's equivalent to 1 because it's an integral multiple of pi. Therefore 2 pi is minus 1, and the lower limit, because the minus sign it becomes plus, e to the power of minus jn pi, because t naught upon 2 multiplied by omega naught equals pi, leads to pi. Therefore this can be written as minus jn omega naught t naught. These two can be combined into 2 times e to the power of minus jn pi and minus 2, therefore 2a times e to the power of minus jn pi minus 1. And e to the power of minus jn pi is either plus 1 or minus 1 depending upon the value of n. Therefore if n is even, this becomes 1, therefore this leads to 0, 1 minus 1. If n is odd, then e to the power of the angle is an odd multiple of pi, therefore this minus 1. So you have a minus 2, minus 1, minus 2, therefore it will become, this j can be taken out, therefore this will become minus 4a divided by n omega naught t naught and a j in front, and omega naught T naught is 2 pi, therefore this will be minus j 2a by n pi. For n naught. And since we know that Cn equals An minus jBn by 2, therefore what we now see is Bn upon 2 is 2a by n pi. From this we conclude that Bn equals 4a by n pi, a result which we already have obtained from the trigonometric form of Fourier. So this ties up with that. C naught of course is 0 because the average value of this is 0, and it's when you are carrying out this analysis to find out the Cn, it would always be advisable for us to arrive at the C naught value independently rather than the state formula of substituting n, because sometimes when n equal to 0 it leads to some difficulties, some degeneracies, because n may come in the denominator. So it is always advisable to calculate C naught independently rather than substituting n equals 0 in the general formula. Sometimes it may work, sometimes it may not. Now we have discussed symmetry conditions in relation to the A and B coefficients. Now what are the similar conditions that are applicable to the Cn coefficients? So let us now discuss that. If f of t is even, we said that only the cosine terms are present, that is an terms are present, not the bn terms. Since we know that Cn is an minus jbn by 2, if f of t is even, it means that Cn is real, because Cn is an minus jbn upon 2. So if bn is absent, then Cn is purely real. The angle associated with the complex number is 0. If f of t is odd, then of course Cn is purely imaginary. We have the bn terms but no an terms. And if f of t exhibits half-wave symmetry, then as before we have only the odd harmonics present. Cn can exist only for odd n. Even harmonics are absent. So to summarize what we have done in this lecture, we started with an example in which we have taken a half-wave rectified sine wave, found out its Fourier series, making effective use of the symmetry conditions. We saw that a half-wave sinusoid can be expressed, broken up into its even part and odd part. The odd part was a pure sine wave. The even part was a full wave rectified sine wave, where whatever waveform is there in one half cycle is reproduced, and therefore we have only the even harmonics present, and we have found out the Fourier series expansion of the even part and odd part separately, and use such a kind of waveform in a practical circuit consisting of an R and C, a rectifier circuit, and use that example to illustrate how we can make use of Fourier series in analyzing the steady state performance of a simple RC circuit. Then we took up the question of Fourier series expansion in terms of exponential functions. So in terms of exponential functions, we expressed f of t as a summation of various terms, each term being of the form Cn e to the power of j n omega t, j n omega naught t, where Cn is a complex coefficient in general, which is related to the a and b coefficient that we already talked about as Cn equals an minus jbn upon 2. And we found out that the expression for calculating C of n is quite surprisingly simple. It is simply the average of f of t times e to the power of minus j n omega naught t, valid for all values of n. And we said that expansion in this form is useful for us when we later go to the Fourier integral form, apart from its compactness and the fact that we have to calculate only one set of coefficients, that is Cn coefficients, instead of having to calculate an and jbn separately. The price we have to pay for that is, of course, we have to use complex algebra because Cn is a complex number, whereas if we are calculating an and bn, we have to deal with real functions only. So we have to pay a price for it, but nevertheless it leads to a very compact notation. So we have two alternative ways of expressing Fourier series, one in terms of the an and bn coefficients, other in terms of Cn, and one can always convert one set of coefficients into the other. We took up a square wave as an illustration and showed that the expansion in terms of Cn will, of course, naturally, as we expect, leads to the same results, but of course Cn now is an imaginary quantity. That means this is related to Bn, which is 4a by n pi, which we already found out. And lastly, we talked about symmetry conditions in terms of the Fourier coefficients of the trigonometric expansion or the exponential expansion, and we said if f of t is even, Cn happens to be real. If f of t is odd, Cn is purely imaginary. And the half wave symmetry, which we already discussed with, doesn't yield any new surprising results. Of course, we know that once the f of t equals minus of f of t plus t naught upon 2, which means that the wave is reproduced with a negative sign in the succeeding half cycle, then the only even harmonics are present, and therefore Cn can exist only for odd n. Some of these, for some odd values of n, Cn may not exist also, but if at all it can exist, it can exist only for odd values of n.